liquid in the reactor. You don't do that. You boil it and then you feed it as steam. So most of the time you're not going to have phase change. Yeah?
Why does TR matter though? You have TR there. Wouldn't you just move your TR to, couldn't you theoretically just move your TR to after the phase change and then they still cancel?
I know what you're saying, but when you're actually solving these problems, you need to keep in mind TR because that's how you're going to look up a lot of these things. But yeah, I mean, like I know I just mentioned that if you have steam coming in and steam coming out, the phase change cancels out. Okay. So now let's look at the delta H of reaction now as a function of temperature. So what is it equal to? Summation of what? Stoichiometric coefficients times what?
Outlet equities.
And so that's the summation so again we have our references plus the integral from T reference to the temperature CPI dt.
So is all this temperature the exit temperature still, or?
For delta H of reaction, yes.
Okay.
So you can define this as being equal to some standard delta H of reaction so again, this is the standard state and delta Cp is equal to summation nu I times the heat capacity of each species. So to simplify this so that we don't have to deal with the integral, we're going to make an assumption. What assumption are we going to make? Not quite constant, but close. We're going to define some average. Well, yeah, we are going to treat it as constant, but we're not going to take the one or the other temperature. We're going to take the average of the two. Yeah, it should work the same. Because that would indicate that you're taking the area under this curve, which is the same as width times the center point. that's what we do is we take the area under the curve, we divide it by the width of that curve, which is just the differences in temperature. I don't like it either. And we can do a similar definition for a heat capacity between now the inlet and exit temperature of that stream, instead of doing it between the reference temperature and the temperature and just some generic temperature. All right, so back to our energy balance. Yes?
Since it's just an average, couldn't we just compute it as an average as opposed to computing it with the integral over the area?
So the difference between those two is if I had a straight line and I take the area under that curve, I'm going to get some area, right? Now I'm relating to some average heat capacity times some volume, right? And that would work if it were a straight line. But that's if I assume that this was linear. If this wasn't linear though, the definition as written would still work. It would just not give me a linear average of these points. In this case, it would drop the heat capacity down by quite a bit. So in other words, by this definition, it doesn't matter what your shape is. Because the mean is not just an arithmetic mean. It's a mean weighted by the shape of that curve. So it's kind of like taking the solution and backing out a simpler thing to use. But yeah, you do kind of have to use the solution in order to get these mean heat capacities. So you might be like, what's the point? To make your lives easier on homework. So yeah, now we're going to substitute that into here. Yeah. And so again, we get Q minus the shaft work. And now instead of this integral term, we have Cp I hat, it's the second one that I defined over there, times the difference between the exit temperature and the inlet temperature for that stream. The standard heat of reaction plus now this other Cp with a hat times the difference between the temperature and now the reference temperature. And usually, if I have, let me put it another way.
Why are we using average?
Because I can give you that on a homework, and you don't have to worry about integrating the function of Cp over the temperature range. That's it. But as defined, somebody still had to do the hard work. But that somebody isn't you.
Do we use both those CPs for both in and out?
No, it's right here. One of them is defined between the inlet and outlet temperature. The other one is defined between the reference temperature and the temperature of the reaction. And one of them shows up in the heat of reaction term because this is still at our reference temperature, right? This is standard state. So that's why we have to bring it back to the reference. Over here, the standard states dropped out because we had a standard state for the inlet stream and the outlet stream, so it drops out. But it doesn't drop out for the delta H of reaction. Okay, so one feed means that all the inlet temperatures are the same. And that's usually the case, right? Most problems, but not always. Just understand that. All right. Trying to decide how far I want to go.
This looks good, yeah.
This is looking mighty nice right now.
Let's do one thing really quick, and then we'll cut out a little bit early.
We gotta get ready just in case Matthew comes.
We're gonna go buy all the water before it sells out.
Yeah,
Get ready
right.
for Matthew.
I got to blur up my windows.
Yeah. There was a post to the Gainesville subreddit that said Matthew's coming, buy more beer. It might just turn into a bit of rain, but in any case, stock up on beer. I think that's what everybody's worried about. Stock up on beer. All right. If that's 0, and that is 0, theta A is by definition 1. Right, so sorry, this is an example. Didn't really put that on here. Theta B is equal to B over A. What does that mean? What's the magic phrase that I could use maybe on an exam that would tell you that?
Equimolar feed.
No, not equimolar. That would be only if B and A were both equal to 1. This is a stoichiometric feed. Equimolar in this case would be theta B equals 1, because theta A equals 1. And we'll say, whoops, not Q. So all the inlet streams are 0, right? No inerts, no inlet products. And then adiabatic, meaning Q is equal to 0.